All right, good morning. Welcome to the very last week of CS50, Monday. So this Wednesday we have our quiz and the locations that are advertised on the website, and then this coming Friday is our very last lecture. Do tell your friends. A couple of announcements. So I will be holding last-minute opportunities for Q&A before the quiz tomorrow night from probably 7 p.m. till 10 p.m. We don't yet know the room, so check the course's homepage sometime tomorrow before dropping by if you would like. Quiz 2 is Wednesday, last lecture Friday, and finally, those of you guys who are interested in using PHP and or MySQL and or XHTML and or CSS for your final projects and would like to host those projects on a more flexible system than people.fas, you are entitled, if you would like, to an HCS account, which those guys have been kind enough to offer up. Simply go to cs50.org/HCS to request as much. So today we're joined by Professor Matt Welsh, who is the instructor for the famed Computer Science 161 Operating Systems course. But he's here today to talk about a brand new course, CS61, which in a nutshell is not CS161, which is to say that this course is very much meant to be accessible to all of you guys, whether or not you've done the hacker editions of the problem sets this semester. And I can say without hesitation and completely genuinely that I wish this course had been offered when I was a student here. It looks honestly completely awesome. So with that said, Professor Matt Welsh.
Thanks, David. Hi. My name is Matt. I'll be your substitute teacher today. So basically what I want to talk to you about is a new class that we're offering in next semester called CS61. And this is all about how do you get down to the nuts and bolts of how computers really work. Okay? How do you get down to programming at the machine level? How do you get down to using assembly language? How do you understand the performance of your programs? How do you understand what happens after the C compiler takes your code and gets it running on a machine? And I'm going to try to motivate this through some examples of, why would you want to understand this stuff? Why would you want to take a class like this? And try to encourage you all to take this class next semester. All right, so I see today's the 10th, right? We're now 3 days in the future. All right, so Tuesday, Thursday, 2:30 to 4. This is the basic thing you got to remember. Prereq, you're all satisfying the prereq as long as you, I guess, pass this course. Or if you haven't taken CS50 for people who are not in this room, if you have C programming experience, you're good to go. CS61, it's a new class, and so where it fits into the requirements, basically it satisfies the breadth requirement for the CS concentration. So CS concentration says something like you got to take I think 3 courses with different middle digits. Yes? All right, CS61 satisfies as though the middle digit were 6, even though there's only 2 digits. So it's like CS061. Does that make any sense? Okay. And also, if you want to do the CS minor, the secondary concentration, you can take CS61 as one of the 4 classes for the minor as well. So there's no excuse not to take 61. And if you're thinking about taking CS51, I really do think, and the idea here is that you should take both of these classes at the same time, especially if you're thinking about it being a CS concentrator, that you're going to need both classes down the line in terms of how the prereqs settle out. So they're designed to go together, sort of hand in hand, and I'm going to talk a little bit about that later on. Okay. So what's the class all about? This is about revealing the mystery of how machines really work. And if you're used to programming in C, C is a language that's very close to how the machine operates. You're dealing with low-level things like local variables and malloc and free and loops and all those kinds of things. And I think you had a lecture last time on Lisp and different programming languages that abstract away the machine even further from where C is. So if you want to think about it, you're sitting in 50. CS51 is going to be about raising the level of abstraction up, going higher up the stack, so to speak, so that you can abstract away some of the messier details of how machines really work. CS61 is about going down and understanding what happens below you, below the level of writing as a C programmer. So getting under the hood and learning how the machine really works. Okay. The other thing that 61 is about is understanding what affects the performance of programs. And this is incredibly important if you're somebody who wants to write code that's going to be as fast as possible. And that's, if you're going to work at a place like Google or Microsoft, or if you're going to be a scientist, a physicist, or a chemist, or a biologist, you need your code to scream. It's absolutely essential that you write efficient code, right? So you might be surprised to find out some of the things that happen at the level of the processor that impact the performance of your programs. Okay? Just to give you a quick example, I can write a loop, and depending on how I write the loop and exactly what order I access variables inside of the loop, I can get a factor of like 4x or 6x performance speed up just by rearranging some of the things in my C program to make it faster. Not by doing anything that's obvious, by doing things that are subtle and that lead the compiler to generate faster code for you. Okay, these are really important things to understand. Another thing that we're going to talk about in the class is processes and threads and synchronization. So most of you are probably aware, I see a lot of MacBooks and stuff around. They all have dual core processors, right? What does that mean? Any idea? What does dual core mean? Basically, there's two processors on one physical chip. So it's equivalent to having two CPUs. Well, how do you take advantage of having two CPUs? By browsing Facebook and chatting at the same time? Not exactly, right? That you need to write applications that can do multiple things in parallel. And that's really tricky. That's really hard stuff. Okay? But if you talk to people in the computer industry today, they're going to tell you the speed of individual chips is not increasing as much as it used to be. Okay? That the chips are not individually getting faster. What they want to do is they want to give you more chips. So if you talk to Intel, they're not going to say, okay, next year we're going to release a 5 gigahertz processor. We're going to release a 2.6 gigahertz processor that has 4 cores on it. Okay, so more parallelism rather than more clocks, as it were. And how do you exploit that? You have to write code that can take advantage of that by forking off multiple little jobs that you want to run in parallel and that synchronize and work together. Does that make sense? Okay, so the way you do that is by using something called threads, which is a whole abstraction for writing parallel code inside of a program, and we're going to have a lot of stuff about that in 61 as well. Okay, so why do we want to present 61? Why are we introducing this new class at this time? And the reason that we're designing CS61 right now is there seems to be a big gap between the concepts that you learn as a programmer and the reality of what's happening on the machine. And many of you will find that out in industry especially that there's actually been a shift away from programming languages like C. Largely, most industry jobs, you're going to program in a language like Java. And Java is a language that is so abstracted away from what real machines are doing because it's intended to run on any processor, on any machine. Yeah? Okay, it can run on cell phones, it can run on laptops, it can run on alpha chips, it can run on x86 chips, it can run on MIPS, it can run on lots of different processors. So they can't tie the language too closely to one machine. Does that make sense? Okay, so what they've done in Java is they've made it easier to be a programmer, but harder to get good performance because it's so abstracted away from reality. Yeah, so there's a gap. And so what we want to do in CS61 is reveal the true nature of the machine sitting below your programs so that you have a deep appreciation and understanding of all of the issues going on at the machine level so that when you're sitting there writing your, I don't know, your fast algorithm for extracting sequences of genes for the Human Genome Project, say you're somebody working on that kind of project, you want to get the best performance possible because you increasing the performance of your code by 50% could be the difference between your research collaborators getting their paper published in the journal that year or the next year. It does matter. Yep. So when you're sitting there and you may be coding in Java or C++ or some language like that, you still need to understand what's going to make that program as fast as possible. I hope that makes sense. Okay. You also need to understand this stuff if you're going to go on to take more advanced courses in computer science. And if you're going to take operating systems or databases or processor architecture or compilers or networks, you do need to have an understanding of the machine level details before you can do that. Just to give you an example, if you're going to be a compiler person, if you're going to take the compilers class, what does a compiler do? It takes a high level language and maps it down to machine code. Well, if you've never seen machine code before and you don't know what it looks like, you're going to have a much harder time doing that. Yeah? Okay. And even if you don't want to be a computer scientist, we think that this is a class that will appeal to a lot of people who don't even want to be computer scientists, but just want to go and write rock solid and fast code. And we're going to teach you how to be a really damn good C programmer in this class. Okay? Crap. Okay, you know this is a joke, right? Because I'm running a Mac. How many of you have seen this before? on your own computers. Yes? And what do you do when you see this? Swear, and then hit the reset switch. But have any of you ever tried to read this thing? This means something. This isn't just gobbledygook that Microsoft throws on the screen to scare you. Okay? It means something. If you look at it, it's saying, well, I mean, we could look at it. Unhandled kernel exception C000047 from FA whatever this thing is, right? Okay, what does that mean? Well, you'd have to understand something about how Windows XP works internally. But what it seems to be telling you is that at some address, there was a memory bug, and it caused the machine to crash. And it's dumping a lot of information about what's in memory at this time and where things are laid out in memory, so that someone who is a operating system designer, somebody working at Microsoft, basically could use this information and understand what's going on. So the point is, you shouldn't be scared of this, because you should be able to look at it and understand what's going on and make some sense of it. And it might tell you, for example, if you looked at it carefully, oh, wait, this might have something to do with that new, I don't know, USB driver that I downloaded last week. Maybe there's a bug in that USB driver and it's causing my machine to crash every time I plug in the camera. Yeah? So I should uninstall that driver and then see if there's an update somewhere. It might actually help you just as a user as well. You guys are coding in C in this class. How many of you have seen core dumped? Like this week. Everyone, right? All of you have seen this. What's a core? Why is it being dumped? Where's it being dumped to exactly? Okay, so this happens all the time. And what's happening is your program is causing something bad is happening, and the operating system's going, wait a minute, you're trying to do something bad here, something you're not supposed to do. I'm going to prevent you from screwing up memory, and I'm going to kill your program, and I'm going to take an image of everything that was in memory at the time it was running and write it out to disk so that you can go and look at it later. How many of you have looked at a core file? You use GDB and try to step through? Great. Okay. So, but the core file has basically an image of everything that was in memory at the time that your program crashed, and that's extremely useful information. So say we were running our program, and you go into GDB, and you can type GDB, my awesome program, core, right? But how do I figure out, let's say that I was running a program that I downloaded off the internet and it did this, and I didn't have the C source code. Yeah? How would you do anything about it? I guess you just email the person who wrote the code and say, there's a bug, dude. Person might say, well, can you send me some more details? What did you do, or what was it? So we could actually look at the disassembly. The disassembly is the machine instructions for the program that was running, yes, at the processor level. And if we type where in GDB, it says, where did it crash? And it gives us this funny thing, 0x0001FEA in main. That's an address of an instruction in memory, a CPU level instruction in memory. If you type disassemble, yeah, sounds funny. I type that all the time. You disassemble the code, and what's it giving us? It's not giving us C code, it's giving us these funny things. Push, move, sub, moval, call, move, moval, jump. What is this? These are the instructions that the x86 processor understands to execute. x86 doesn't understand C. It understands this much lower level thing. This is assembly code. Okay? And if you know how to read the assembly code, you might be able to find the bug and understand what's going on with the program, even if you don't have the source. Right? And I can't tell you how many times I've had to go and look at assembly code, even though the code I was writing the program in C, but it wasn't doing what I thought it was doing. I didn't understand there was a bug, it was crashing. But I look at the assembly code and I go, there's something going on. Because one line of C, seemingly innocuous line of C, could turn into, 50 instructions on the machine that might be doing something funky that you didn't quite think it was going to do. C gives you a lot of rope to hang yourself with. It really does. You can do so many funky things in C that, it looks like it's the right thing, but it ends up not being the right thing. So in this case, if we look at, this is the place it crashed, and then we go down here and we look at that. Okay, that was the instruction. And what is it saying? It's saying, move the value 42 into the value pointed to by the EAX register. So it's copying a value into a memory address somewhere, and that caused the machine to crash. Well, what does that tell us? Maybe that memory address was a bad memory address. Yes? So what could I do in a C program to cause that to happen? Great example. So I might have an array that's 10 elements wide and I try to access the 11th element. Right? There's no guarantee that there is the 11th element because you only allocated 10 elements. Yes? Okay. By the way, doing exactly that, accessing stuff off the end of an array is exactly how we crack into machines a lot of the time. That's how the iPhone was jailbroken. You guys talked about that. Mike Smith came and talked about, there's been innumerable viruses and worms and things on the internet that all exploited the fact that our C programs don't check when we're going off the end of an array sometimes. And if I can put something in memory that was not supposed to be there, I might be able to get the machine to start executing instructions on my behalf. One of the assignments in 61, you're going to do this. I'm not kidding. We're going to give you a C program. It's going to have bugs in it, and you're going to have to exploit the bugs to get it to run your code. We're teaching you to be little hackers. Yeah? All right. So let's do an example of that. Let's say that I put a program in my home directory. Let's just imagine I did this. I put a program in my home directory basically for my students. I want my graduate students to run programs as me, because sometimes they're emailing me saying, oh, can you fix the permissions on that file, or whatever, right? So I want to let them run commands as me occasionally, but in order to do that, they have to know the password. Not my password, but I'm going to give them a special password. So they run this program called MDW shell, and it asks for a password. If you type the right password, it runs a shell as my account. Does that make sense? Yes? So say you looked in my home directory and you saw this interesting program called MDW shell. You don't see the source code for it anywhere. But there's a binary. Could you figure out what the password is? How would I do it? I need to look at the binary. I could guess every possible password, but I've made the program a little more clever. So if you guess every time you guess wrong, it emails me and says that you guessed wrong. So don't do that. So I only have one try to get this right. So I want to look at the binary and figure out what the password is. Does that make sense? Yes? So let's look at the binary. Cat MDW shell. Okay, no, it's this ugly thing, and actually, so it looks like there's some English text here. But then it's this stuff with umlauts, and this is not heavy metal. This is, this is machine instructions, but machine instructions don't map onto ASCII characters all the time, right? So it's printing them as Y's with dots over it. But this is basically, like I'm just by looking at, okay, this doesn't make any sense. This is gobbledygook, right? So what if we looked at it in hex format instead? So I can use a program called OD to dump out the contents of a file and look at it in hex. Well, this doesn't make a lot of sense either. Anybody read that? No? You can't read that? I can't read this either. But if we use a disassembler, then we can look at the machine instructions that this represents. Disassembler can read this and dump it out as machine instructions. So I can look at that obj dump. I'm giving you the tools to be hackers today. Okay? Use them wisely. Okay? This is how it all begins. So if you type obj dump and give it a binary, it'll give you the machine instructions in the binary. And this means something. And if you know x86 assembly language, you can read that. And if you go download from Intel a copy of the x86 programmer's manual, it'll tell you what each of these instructions does. Push, move, sub, move, jump. Yes? Now some of them seem kind of obvious. Move, that's copying from one thing to another. Sub, subtraction. Yeah, jump, it's jumping to a new place in the program. This is what's happening at the machine level. This is the code generated by the C compiler. So let's say I'm looking at, okay, do I want to figure out what the password is in this binary so I can hack into my own account? Yeah? So what I do is I look at the binary. Let's just take a look at some of the instructions here. Well, looks kind of complicated. What is this doing? Well, if I go and read the manual, the x86 manual, and I learn the assembly language instructions, I can figure out what they're doing. The first ones is putting something on the stack, it's copying a stack pointer, it's subtracting 20 bytes, it's moving this to a register. Okay, we don't need to understand the details of this today, but this does have meaning. Okay, so it looks kind of complex, but if you take CS61, you're going to understand this stuff. It's actually not very complex, it's incredibly simple. There's one instruction here that kind of jumps out. This one right here. It says move, and it gives this value into EAX. And then it seems to do later in the program, I'm not showing you, it seems to look at this, the contents of memory at this location. Yeah? So that might, you know, this is a routine that's looking at a password. So you might think this is telling us something about where the password is in the binary. Does everybody see that? Yes? So the program's paying a lot of attention to this memory address right here. So let's go take a look at what's at that address. Well, so if I look at that address, and I can just use objdump again to look at that. This is the contents of memory. This is the value 8049808, and then up here, this is 8049814. This is what the program was looking at, this value right here. Well, does that look like a password? It doesn't look like a password to me. But if we look at it, how do I decode this? How do I read this? Well, you got to understand something about how the processor stores values in memory. And it turns out that the x86 processor, if you give it a 4-byte value, it stores the lowest order byte first in memory. Have you all heard about this? Little Indian, Big Indian? Yes, this is called a Little Indian processor. So if I have a 4-byte value, the first byte, the lowest order byte is stored first in memory. The highest order byte is stored last in memory. So in other words, when I'm reading this, this is the first byte, second byte, third byte, fourth byte, but I have to reverse their order in order to read it as hex. So this value, AC860408, is equal to 080486AC. All I've done is I've reversed it. Does that make sense? Now, if you didn't know that the x86 was a Little Indian processor, you wouldn't know to do that. It would lead you astray. Well, look at that. That value, what's this value here? 80486AC. That's interesting. Why? That looks sort of like a memory address, because this is a memory address, yeah? So it's about the same value, so that's probably another memory address. Well, let's go look at what's there. Yeah, we'll go use objdump again and look at the binary at that address. And if you look at it, this is the value in hex, and I'm sorry, it's not coming out. Who can read that? Aha, yes. Okay, so that must be the password. And yes, indeed, if you run this program and you type take CS61 as the password, it'll run a shell as me. Okay? So the reason I'm talking to you about all this is because if you understand the tools and you understand what's happening at the machine level, you can do some pretty incredible, nefarious things. Yeah? So I've opened up a contest to get you all excited about this idea. It's called Hack This Binary. And if you go to the CS61 webpage, there's a link there, and it'll lead you to instructions. There is a binary on the fast machines, and if you can guess the password, the first one to do it is going to win a prize. I don't know what the prize is going to be yet. Something good. Yep. And some of you with laptops are at more of an advantage because you can start now. So if you look here at the this is the CS61 webpage. Yes? And right at the very top, it says, click here for information on the CS61 binary hacking contest. Click there, and it'll tell you what to do. Okay? Everyone who guesses the password is going to go onto a Hall of Fame list. And I will tell you right now that it's a bit harder than the example I just gave you. It's a little bit harder. You can't just do what I just showed you what to do. You have to do something slightly different. So you have to look at the program, figure out what's going on. The source code is not there, just the binary. I want to talk to you a little bit about a wonderful anecdote, and David's passed out Reflections on Trusting Trust. You should read this at some point. This is one of my favorite stories from computer science. Ken Thompson, that's a picture of him there. He's not as good looking as, well, for example, Professor Malin, but pretty smart guy anyway. And you know, he co-invented this thing called Unix that I'm sure you know about Unix. Yep, you use Unix every day. Okay? And in 1983, he won the Turing Award, which is like the CS version of the Nobel Prize. All right, big deal. And during his lecture, so he it's like the Nobel Prize. You win the award and then you give a lecture about something interesting that you want to talk about as part of the award ceremony. He made this stunning admission. This is just fantastic stuff. So in the early days of Unix, he wanted to be sure he could log into any Unix system that was out there to debug it. Now remember, there are only a handful, but he wanted to be careful. He wanted to be sure, even if the person running the computer changed all the passwords, that he would be able to get a backdoor and log into the machine himself. Yes? So he hacked the login program, the program that asked you for your password, to accept a magic password that he put in there. Does that make sense? Yeah? Simple backdoor, right? Now the problem was that everybody had the source code for the whole system. So the code for the login program was just in the clear. Everybody had all the source code. It wasn't like today where you get the OS from Microsoft or Apple or something and you don't get the source code. Right? Yes? So he knew that if he just put in login.c, if the password is, foo, login, that everybody would see that backdoor was in there. So how did he hide it? He had to hide this somehow. So here's what he did. He hacked the C compiler. He wrote the compiler also. That's the thing. It's kind of, right, So if you're also the person writing the compiler, you can do these things. He hacked the C compiler to recognize when it was compiling login.c to add the code for his backdoor in there. Does everybody see where I'm going with this? So if you looked at login.c, you would not see the backdoor code. Questions? Nobody's asked me any questions today. You're welcome to stop me and ask questions. I don't remember. Actually, it may be in the article, but I don't know if he ever revealed it. It was the 60s, so, pick something. All right, so this is great, right? So if you look at login.c, you don't see any backdoor, but if the C compiler is compiling login.c, it's emitting the code for the backdoor when it generates the login binary. So you're tainting the login binary through this tainted compiler. Yeah? Okay. Well, what's the problem with this? Any idea? I mean, this works, but what's wrong with it?
Just look at the compiler's code.
Okay, so now the problem is the compiler source code. Yes? Was available to everyone. So he hacked the compiler to recognize when it was compiling itself to add the backdoor code for login.c into the compiler. I know it's like 10:30 in the morning and your head hurts already, but does this make sense to everyone? Does everybody understand what I'm saying? That the remember, the C compiler was written in C. So that meant that when you make a change to the compiler, you use the old compiler to compile the new compiler. Now, we have a chicken and egg problem, yes? How do you get the first C compiler? Before you had a C compiler, you couldn't compile the C program to, yep, okay, yes, it's complicated. So the first C compiler was probably written in some other language, some older, crappier language that they didn't want to keep using. So that's all new compilers start, is when you want the compiler to compile itself, what you have to do is you have to write the first version of the compiler in some other language, get it up to the point where it can compile a simple C program, and then you write the new compiler in C and the old compiler compiles itself. Yes? It's really complicated. Yeah? So what he did was he changed the C compiler to recognize when it was compiling itself to add the backdoor code for login.c into that login binary. And then he deleted the original source code for the compiler. No trace of this hack exists in source form anywhere. This is like a James Bond kind of plot. Yeah? Any questions about this? This is cool. This is really cool. Now this is all about self-modifying code, and so his paper, his lecture for the Turing Award was Reflections on Trusting Trust. Who do you trust? I get the compiler, I download GCC from the internet. Did I trust the person who wrote GCC not to do funky things to my program when it was compiling? How many of you have read the code for GCC? I have, but I don't understand most of it. So I can't tell you that there isn't, bugs in there. Yeah? This is way cool. All right. Last topic I want to talk about is just these 3 topics, just to motivate. These are things we're going to talk about in the class. And I'm trying to motivate why you want to take 61, why you want to understand what's happening at the machine level, because these are the kinds of things that go on. So I happen to be good friends with people at Amazon, good friends with people at Google, people at Yahoo. All right, say you are at Amazon or Yahoo or Google. And one of the really most important things there, of course, is handling really massive load. What I mean is we have this phenomenon on the internet, flash crowds. Yes? How many of you read Dig? Or Slashdot? Or any Slashdot? Yes? All right, so how many times have you gone to one of these sites and you click on the link and it says server down? Yeah? And the reason is that 100,000 other people clicked at the same time that you did. Okay? If you're Amazon, you don't do this. You don't want your server to go down when it becomes hugely popular. In fact, at Amazon, they don't tend to track the performance of their site. They don't look at the latency and the throughput and the CPU utilization, the memory usage, and all those things like the low-level, machine-level metrics. You know what metric Amazon uses to know whether their servers are working correctly? Dollars per second. I'm not kidding. So they have a model that says over the course of a day, over the course of a week, how much money should they be making per second from people buying things on their site. And the only time they go and investigate performance problems is if that dips below some expected value. Yeah? So they care about dollars per second coming in. Okay. So this is a really hard problem. I got to write server software that will not fall over even if it becomes hugely popular. A massive surge in demand. The thing about this overload is that it can be orders of magnitude greater than the average load. Okay, so say you're hired at some new internet startup, and they put you in charge of designing their website to making sure that it's going to stay up, and they say, okay, well, we're a new company. This week we have I don't know, 1,000 hits a week or something like that. So can you just make sure that we have enough to handle 2,000 hits a week, right? Because people might start hearing about us. Is that a good idea? No. Because as soon as they get mentioned on Dig or something, the number of people going in can go up by factors of 1,000 or 10,000 or 100,000 in minutes. In minutes. And September 11th was, of course, like the biggest example of this in history. So I was living in California at the time. I woke up and I checked my email. And now it's, it's 3 hours different time zone. So everything had already transpired. I had an email in my inbox from somebody in my department saying, go turn on the television. He didn't say what had happened, just go turn on the TV. And of course, the TV's in the other room. I'm sitting at my computer. So I pull up the web browser. I go to, www.cnn.com. And it's just nothing. Nothing comes back. It's just waiting for cnn.com. Okay, that's strange. CNN's down. Okay, so how about nytimes.com? It's down. I went to BBC. Down. I went to an Australian news agency thinking that maybe this is a local thing. No, it's down. My DSL was working. Yes? So it wasn't that. All the news sites I tried were down. What was going on? At CNN, they had 30,000 hits a second. A second. And it brought their whole site. Now they have it's not one box. It's not like one server is the web server, yeah? They have hundreds of machines acting as web servers. So what ends up happening at CNN's owned by, I think, Turner Broadcasting Company, is that right? Yes? So CNN started taking servers from other, websites that the Turner Group owned and putting them to CNN.com. There's something funny happened that day, actually. There was a spike in load on one of Turner Broadcasting's websites, which was the Cartoon Network. On September 11th, they saw this vast spike of the Cartoon Network website. Why? Any idea? What's that? No, it wasn't because people were mistyping the URL. No, that's a good guess, actually. It's because all the kids had been sent home from school. Right? I mean, whatever, is a Tuesday or so? Was it a Tuesday? I don't remember. Yes? A Tuesday, Cartoon Network's not expecting heavy load. Yeah, okay. A lot of examples of this. So the Slashdot effect, daily frustration to nerds everywhere. All right, so God has done sort of similar kind of Slashdot effect things to websites as well. This is the load from a website at the U.S. Geological Survey following a big earthquake that hit in Southern California in 1999. And this is the load. If you can all see this tiny amount of traffic down here. The earthquake was at 3 a.m., okay? So let's just say this is not a very popular website usually. But apparently there are people, you know, going to the USGS website at 2 in the morning. I don't know who they are. Yeah? Now, this big earthquake happened, and I don't think there's a lot of damage or anything, but it was felt by many people in the LA area throughout the whole Southern California region. So a lot of people felt this jolt or this shake, and if you live in LA, you get very nervous whenever you feel something like that, because it might be, you know, the big one. Is California an island yet? Yes? All right, so a bunch of people jumped on to the USGS website because it shows a real-time map of where the earthquake was and all this and how big it was and all that stuff, yes? So an 1,000 time load spike in a matter of like 5 minutes occurred on this site. And this is incredibly heavy load for what they normally are seeing, yes? And as you can see, the load, this is hits per second on the y-axis, the load kind of eases off, you know, as it goes to 6 a.m., but then it spikes again. Why did it spike again? People are waking up and they felt the earthquake last night, or they might have seen a little blurb on the news in the morning or heard it on the radio and they wanted to check the website. Now, what happened here at 9 a.m.? Yeah, so actually the server didn't go down, but the logs, the disk hosting the logs filled up. There's so many hits that the disk filled up that was storing the logs. Now, I actually emailed back and forth with the administrator of this site a little bit, and he didn't tell me why. So he told me that he was, you know, logging in from home, trying to log in from home telnet to the server from home and clear out the logs in it because he knew like it was a heavy load. But I didn't ask him why it took him 3 hours to get to the office that morning. You know. But he ended up going into the office and plugging in a keyboard and a monitor to the server and fixing it by hand and then rebooting and then, okay? But if you see here, this load, even, you know, 24 hours after the earthquake is still really, really, really high compared to where it was before. Yeah? 10 hits per second. So these load spikes are sudden, they're unpredictable, they're orders of magnitude greater than what you're expecting, and they last for a long time. So designing software to handle that is really hard, and that's one of the things we're going to talk about in 61 as well, how to write really robust, fast systems code. Questions? Okay. So I think hopefully I've convinced you by now about CS61. Why do you want to take it? We're going to talk about learning how the machines really work, how to use the tools, how to be an expert at that level. How to debug. You need this kind of information to debug the hardest and most interesting bugs. I think of assembly language a little bit like Latin. It's unclear that you need to really speak Latin unless like you know, are good friends with a pope or something, yes? But it's not like you learn Latin. You don't learn, Latin is very important to learn, yes? But it's not for conversational use. It's because it helps you understand the structure of other languages and thinking about linguistics and all those, you know, other things. So I don't think you need to learn how to program assembly language because you're going to be asked to write assembly code one day. But there's going to be lots of cases where you're going to have to go look at a dump of some code that you didn't write and try to figure out what's going on. Yes? Or look at a crash report from a program that you did write and fix it. And the only thing that's going to be available is assembly dumps, core dumps, things like that. Okay? Why else do you want to take this class? I've already kind of talked about hacking binaries. Yeah? And there's lots of good and bad reasons to hack binaries. Far be it from me to propose that you do anything unethical. But, you know, how was the iPhone jailbroken? How did the Code Red virus spread so quickly? Code Red was this virus that like took over the whole internet a few years back, and it basically just was exploiting a buffer overrun bug in a very popular Microsoft product. And it took over lots of machines. There was a much earlier worm, something called the internet worm, that took over basically 80% of the machines on the internet in like 3 days. Now, I don't think you want, I'm not necessarily here to teach you how to write those worms. but I think it's important that you understand how they work, how they spread, what kind of a security holes they are exploiting, so that when you're asked to write code, you can make sure your programs don't have those kinds of flaws, right? You got to understand kind of the enemy, so to speak, in order to write better code. Really important is understanding how to measure and improve the performance of your programs. And there are many subtle, kind of unexpected things about how you write your code and how it's laid out in memory that's going to have a big impact on its performance. So you got to understand caches, memory hierarchies, processor pipelines, parallelism. Okay, the model of a processor that you're used to thinking of is not reality. Modern processors are very complex. They're massively parallel. They can run many instructions simultaneously. They can pipeline things. Okay, there's lots of stuff happening inside. And also how to write these multi-threaded concurrent programs like a pro. If you're going to basically work in any industry where you're asked to write server software that's going to sit on the internet, you need to understand how to program in threads. You got to understand how to deal with concurrent requests coming into your software, right? How to synchronize those things, how to avoid deadlocks and race conditions. Okay, so there's lots of things that you need to understand about parallelism. You're used to writing programs these days that are basically one thing that's happening at a time, but in the real world, most programs are massively parallel. There's lots going on simultaneously. Even something like a web browser, if you think about a web browser, that's parallel because as I'm loading a web page, I can click on the stop button, yes? And, 80% of the web pages I look at have some cheesy animation on there, yes? And in the background, I might be downloading a big PDF file while I'm surfing to another web page. So there's lots of parallelism going on in this program. There's not just one simple activity. There's like 10 activities simultaneously, and they have to coordinate what they're doing. Right? Okay. I realize this stuff sounds very hard. And as David said earlier, CS161 is the operating systems class, and it has a reputation as being, shall we say, somewhat challenging. Yes? 61 is not intended to be a hard class. It's intended to be a fun class. It's intended to be a class that you can all take and do very well in. We think that every CS concentrator needs to take 61. We think a lot of people that are not going to be CS concentrators should take 61 as well, because it's a lot of practical real-world stuff that we're going to teach that even if you don't go into CS, you're going to use later in life. Okay? So it's going to be challenging, and we think everyone in this room can and should take 50. The lab assignments are going to be a lot of fun, and you're going to be able to work in pairs on them. The first one is we're going to give you a binary, and it's going to ask you for a password. If you get the wrong password, it emails us, and you get a quarter point off the assignment. Okay? So you can't brute force it. Okay? So it's a binary bomb. In other words, if you don't get the passwords right, it'll explode. Not like literally, but I think there's some ASCII art in there. Okay? Yes? All right? And we're going to give each pair of students a different binary. So there's no way that you're going to be able to share information on this. The passwords you're going to be asked for are going to be different. It's customized for you. And it's going to ask for 6 different passwords of increasing level of difficulty. The first one's an easy one. I already showed you how to do the first one, okay? The second one is like the contest that I'm running now. The third and fourth and fifth are a little harder, but you're going to be able to do it. It's fun. Everybody likes this assignment. Another one, we're going to give you a binary that's got intentional buffer overrun bugs in it, and you're going to have to exploit the overrun bug to cause the program to run code that it wasn't supposed to run. And this is like how all viruses work. Yeah? So Harvard's going to be, a bunch of evil people are going to come out of this class and go off and write lots of viruses. You're going to have to write your own dynamic memory allocation subsystem. Malloc and Free, you use them, yes? How do they work? How are they implemented? How do they work efficiently? Well, you're going to find out because you're going to have to implement your own. Trust me, after that assignment, you will really, really, really understand pointers. Trust me. Yes? You're also going to write your own Unix shell. Shell is the program that you sit in front of and you're typing commands to, but a shell is more than that. It actually is responsible for letting you pipe things together, and you can hit Control-Z, Control-C. You can put things in the background. Yes, so the shell has to manage running, forking multiple processes and coordinating them and waiting for their execution, redirecting things to files and all that kind of fun stuff. The shell does all that. You're going to write your own shell. And the last one, you're going to basically write your own web server. Okay? That's got to accept requests from multiple clients and do something with them. Yeah? And synchronize their activity and run concurrently. So you're going to write your own concurrent internet service. And guess what? I guarantee a lot of employers out there will like it if you can do that. Yeah? Because that's what everybody's doing today. Workload. So there's 5 assignments. And we give you a few weeks for each one, so it's really, we think the workload, and you work in pairs, so we actually think it's really manageable. There's going to be 2 kind of quiz/midterms in class, and the final will be a 24-hour take-home final, and all the midterms and the exams are open book, open notes. Yep. Sounds easy, right? Okay. After 50, you may think this is easy. Yes. Okay. You all know this? Okay. So if you take 51, right, you are going to go up the level of abstraction, and it's very important that you do this. This is not against 51 at all. You need both. You need to understand how abstraction and programming and algorithms and data structures and all those things work. CS61, we're going to show you how deep the rabbit hole goes. We're going to take you down. And I really want to encourage you to, this is not like the matrix. You can take both. And you should be able to take both. The workload is going to be great, manageable, if you take both at the same time, especially if you want to be a CS concentrator. Almost done, almost done. Okay, so just a quick rundown on the syllabus. We're going to start out by teaching you x86 assembly language programming. You're not going to have to write a lot of assembly code. The point is not to ask you to write complex programs in assembly. It's to ask you to make sure you have to read assembly. And the binary hacking requires that you write a little bit of assembly just to get it to do something. But it's not like we're going to ask you to go implement hash tables in assembly language or something. Performance measurement, program optimization, linking and loading. What happens? How does the binary on your hard drive get running on the computer? Yes? Memory hierarchies, caches, dynamic memory allocation. We're going to teach a lot about Unix systems programming. So if you want to deal with files and pipes and terminals and sockets and processes and all that stuff. Thread synchronization, we'll do Unix sockets programming. This is really important if you're going to write any application that's on the internet. You've got to know how to deal with sockets, which is the way you communicate on the internet. And finally, implementing these concurrent servers. Okay, so with that, I'm happy to take questions. And if you are interested in the class and you're not quite sure if you're ready or if you have any kind of questions at all, please feel free to email me. I'm mdw@eecs. Or you can just come by my office. I'm usually in my office. Just knock. If the door's closed, I'm usually in there. You can meet my dog. I'd love to see you all next semester. Have a good time. Thanks.